Chile, and he's at the Texas A&M. I don't know what that stands for, university.
It doesn't stand for anything. It's Texas A&M is a word. A&M is a word. It used to stand for agricultural and mechanical, and now it stands for itself.
Okay, that's interesting. Okay, so you have 45 minutes, and then we will have 50 minutes for questions.
Okay, great. Well, thank you very much for coming out to listen to me. Thank you very much to Rodrigo and Guido for inviting me back to Santiago. I think I came here for the first time about 15 years ago, and it's a pleasure to be back. So I want to talk about affective science. I was told that this was going to be primarily a workshop a conference on cognitive science. So I thought I'd introduce you to some of the things that I've been working on in connection with the new edition of my textbook on cognitive science. And we've been sitting here for 3 days, and we haven't really talked a whole lot about affective states or emotions. And I think that's a shame, because this is one of the most interesting areas in cognitive science. And looking at affective science gives us the opportunity to think about aspects of the mind and aspects of cognition that have typically been ignored by cognitive scientists. And it also allows us to look at some tools that are not as well known as they could be, and some of them are very, very, very modern, and that they allow us to study the mind at different levels of spatial and temporal resolution. So, one of the reasons I'm interested in affective science and affective states is because it gives us a way of moving beyond a very traditional conception of psychological states. And the traditional conception of psychological states is very deeply embedded in traditional representation-based cognitive science, represented by people like Fodor, folks that Philip was talking about in his in the open forum, the round table yesterday. And what we see in contemporary affective science is, instead of thinking about psychological states as discrete content-bearing entities, we see them conceptualized more as areas in multidimensional space. And we also see a much closer integration of animal work, reflecting the evolutionary sort of primitiveness of emotions and other affective states. And we see a whole bunch of new tools, particularly tools from genetic engineering, that you may not be familiar with. So, some early theories. The early theories in thinking about emotions were very continuous with traditional cognitive science. So, you may have come across, for example, Ekman's basic emotion theory based on facial recognition studies in Papua New Guinea and various other places around the world. And he sort of converged on this idea that there's a small number of basic emotions that are common across cultures. They're effectively cultural constants. Herbert Simon, one of the founding fathers of cognitive science, one of the prime drivers behind the computational model of the mind, had a theory of emotions, and he thought of them as essentially interrupt mechanisms. So they're ways in which a computer program, or the mind considered as a computer program, could disengage from one program and lock into another, or suspend activities depending on external stimuli to deal with time-sensitive kinds of issues. So he saw emotions as essentially a response to a set of computational problems. And things have moved on, fortunately. And so what we have in more modern affective science is a much wider range of affective phenomena. And we can think about them, and I'm going to give you a little table in a minute that shows that attempts to clarify some of the stuff that's going on here, because often when people talk about emotions and affective states, they confuse a whole bunch of different things. Sometimes they're talking about emotions, sometimes they're talking about feelings, sometimes they're talking about moods, sometimes they're talking about the language that we use to describe all these things, sometimes they're talking about the judgments that people make about how concepts are to be applied. So I want to try and impose a little bit of order, but my main point is that there's a huge kind of menagerie of different psychological phenomena here. And the boundaries between them are really blurry. And that's kind of one of the main drivers why affective scientists typically think about affective, very irritating. Why they think about affective states as points in a multidimensional space. So here's a sort of rough typology of some of the stuff that people talk about and people study. So often when people talk about emotions, they're talking about relatively short-lived states like anger and joy, typically lasting for seconds or minutes, primarily operating on actions. And sort of wrapped up in those are emotional feelings, so having a knot in one's stomach, for example, even shorter term, seconds or minutes, and their job is kind of to make agents aware of the emotional states that they're in. A lot of the experimental work in this area actually confuses emotions and concepts of emotions, which are obviously things that we deploy in thinking and communicating about emotions. There are also dispositional states, emotional traits, irritability, fearlessness, things that manifest themselves in different types of actions and susceptibility to different feelings and different emotions. Different from those, again, are moods. Depression, for example, lasts days, months, years. And these operate primarily on cognition and on overall sort of somatic and psychic tone, but also indirectly on actions. Then we've got instincts, infant crying, avoidance of painful stimuli, and so on, short term. And I think of these as innate, kind of like innate responses to specific environmental triggers. And then we've got drives, homeostatic drives connected with sex and hunger and thirst and so on and so forth. So this is a sort of partial map of the kind of things that exist in the sort of emotional and affective landscape. And you can see, with just looking at these, that they don't really form a simple, straight, linear continuum. There is no sort of obvious overarching category in which these are all different points. So that's why people tend to have started thinking much more in terms of emotions and emotional states as being points that are fixed by their values on multiple directions. So the simplest model in this area, which you may have come across, is called the circumplex model. And according to the circumplex model, there are basically all emotions can be all emotional states, and these include moods and feelings and stuff. They can all be located relative to two dimensions. A dimension of valence, basically how pleasant or unpleasant this state is experienced as being, and a dimension of arousal, basically measuring your degree of physiological and psychological engagement and responsiveness. So you'll see, for example, that we've got right down at the bottom, you've got moderately things that are neither unpleasant, low affect states that are neither pleasant nor unpleasantness. As you go up in a clockwise direction, things become more unpleasant and more active, higher degree of arousal. And this is pretty popular, but it's kind of hard to really expect all those things that I put on that table to be distinguishable relative simply to two dimensions of valence and arousal. It's hard to think, for example, that every negative state is going to be distinguished by different levels of activation. So if you think for maximally unpleasant fear and maximally unpleasant anger, according to the circumplex model, the only way you could distinguish them would be relative to the dimension of activation or arousal. And it seems perfectly possible that there could be states of fear and anger that are clearly different, but similarly unpleasant and similarly activated. So some other people have given more complex sets of dimensions for helping map affective space. And by the way, this idea of thinking about mental states as points in a multidimensional space is very, very, very germane to, very consistent with connectionist parallel distributed processing neural network psychological models. But Adolphs and Anderson, two very, very influential behavioral neuroscientists, they identify seven dimensions on which affective states can vary. So scalability, which really measures intensity. Valence, which is a measure of pleasantness or unpleasantness. Persistence, so the extent to which an emotional state will outlast the stimulus that elicits it. Generalization, how they generalize over stimuli and behavior, as opposed to being simply fixed responses. So you can think about this dimension as having fixed responses here and things that generalize maximally out there. By global coordination, they mean that the extent to which emotional states engage the whole organism and have wide-ranging physiological and psychological expressions. Sorry, I keep this. It's a little frustrating. Anyway, so we're down on 6. So global coordination, engage the whole organism, and then automaticity, they can be challenging to control and to regulate. And a lot of the research into the cognitive science of emotions is really about studying emotional regulation mechanisms, and we'll look at some of that in due course. And then another dimension of variation is what they call social coordination. So the extent to which affective states kind of serve a signaling function. Signaling to conspecifics and to members of other species. And how they work to get different organisms to work in a coordinated and integrated manner. And then there's another multidimensional approach associated with cognitive appraisal theory, which is another approach to emotions that are pioneered by Lazarus and some other folks. So here we've got a slightly different set of dimensions, and just drawing your attention to most of those are similar to the ones in Adolphs and Anderson, but they also talk about the appraisal tendency, so how you're interpreting these things to which you are emotionally responding. So, for example, they think that anger is an emotion that typically involves seeing external events as predictable and under human control and created by other people, whereas fear is one that involves seeing them more as unpredictable and not under situational control. I hope I hope my copy editor picked up that missing word there. So, again, the point I want you to take away from this is not the specifics of circumplex theory or Adolphson Anderson's theory or cognitive appraisal theory. What I want you to take away is this idea that people are thinking and studying emotions and other affective states as points in a multidimensional space, and looking to see how those how they vary according to those different dimensions. And you can hold some dimensions constant and manipulate other ones, or manipulate the external circumstances and see what dimensions are altered by those manipulations. And there are some interesting implications, I think, of this multidimensional approach. And by the way, just a sort of passing comment. So I published the first edition of my textbook on cognitive science in 2010, and Philip knows because I was working on it when we were working together at Washington University. And it's kind of been interesting to me. I'm now preparing the fourth edition, what things are sort of moving out and what things are moving in. And when I wrote the first edition, it was really heavy on representational theory of mind, representations, Fodor, causation, all that kind of stuff. And that's slowly dropping out. And it's becoming much more neuroscience heavy, much more neural network heavy, much more looking at alternative conceptualizations of the mind, instead of this very traditional idea that there are causally efficacious discrete entities that are content-bearing, the sort of thing that has underwritten the traditional philosophy of cognitive science and traditional cognitive science for a long time. So I think that I'll soon be starting on the fifth edition, and my prediction is by the time I get to the seventh edition, I think that Fodor will no longer be in the index. He's already lost a lot of references. So that was my aside. Back to the talk. So implications of the multidimensional approach. I think it allows us to study emotions independently of emotional concepts and linguistic expressions of emotions, because we can study degrees of affect, we can study observationally degrees of social coordination. And it's very much an alternative to the kind of approach that was taken by Eckermann. You know, you tell people a story and you say, well, point to the picture that most represents the emotional state described in the story. And this is kind of crude. There's lots of confounds. You don't really know whether you're studying people's understanding of emotions, whether you're understanding socially constructed expectations, what's going on in the interpretations of the stories. It's not as scientific as one might want. And so here we've got individual dimensions that are scalar, so you can measure them and you can manipulate them. And I think it also reflects the fact that affective states blend into each other. And they're much more fine-grained than emotional concepts might suggest. So there's no reason why you should know about this or even care. But one of the things that I've been working on for many years in philosophy is this idea of non-conceptual content. And the idea that there are aspects of experience that far outstrip our conceptual tools for describing them. And I think emotional life is something that really is a great case for analysis in terms of non-conceptual content. And I kind of regret not having seen that, 20 years ago. But still, it is what it is. And it also allows us to break affective states into different areas of study, some of which you can pursue with non-linguistic and non-human animals. So if you think about 7 dimensions, let's say, and then you accept that there might be values of 0 on some of those dimensions, you can study the other ones in isolation in non-human animals, and that those 7 things that I pulled out from Adolphson Anderson actually is from a book they wrote popularizing some of their really groundbreaking research. And they have a lot to say about the emotional lives of insects. So here's a graphic that I think represents this kind of general approach to emotions. So I tried to think about what a general episode of an emotional episode might look like, and what the components are that are constant across the whole hierarchy of animal and insect life, and which ones are more specifically human. So you're always going to have some sort of triggering stimulus. Well, not always, because depression is kind of a little untriggered. There's always going to be some sort of context and complex interplay between them, and I really hope that copy editor picked up that F as well. And then there's going to be some somatic responses, so skin conductance, sweating, decrease in temperature at the peripheries, clearly a neural signature, a distinctive neural signature for many different types of emotional state, or even for specific dimensions within emotional states, and behavioral responses. So these are things that you're going to have, whether you're a fly or Guido. But then you've also got the cognitive appraisal dimension, the emotional feelings, and the verbal responses and the conceptualizations, which can be studied independently. So, if you think about emotions in this multi-dimensional sort of way, it's helpful to, and you think about an emotional episode in that way, then you can see that there's really a huge kind of toolkit that we've got for studying emotions. So if we want to look at the neural responses for each of those little dimensions back on this graphic, if you want to look at the neural responses, then you can study those with some of the things that we're familiar with, and electrophysiology, single neuron recordings in monkeys and other animals. We can use neuroimaging. It's actually really hard to do neuroimaging studies on emotions, and I'll explain that in a little bit and talk about some of the kind of cool things that people have done to allow neuroimaging of emotions. You can also do some really cool genetic engineering and use genetic tools to change neural profiles so that you can effectively knock out responses on particular dimensions. And you can also use genetical engineering tools for measuring neural activity at the level of populations in neurons. So we'll get to those in a minute. And then you can also use your good old-fashioned lesion studies in human beings, but also experimentally induced in animals, some of them reversible, some of them not so reversible. And then when you're looking at the somatic responses, when you're looking at this stuff here, then you can use your standard measures, your galvanometers and so forth, to measure skin conductance, body temperature. We've got good tools for studying facial expressions. And then we can use the whole toolkit of stuff from cognitive psychology and social psychology, self-report, FACS, which is the, what is it? I've forgotten. It's an acronym that measures a standardized way of describing facial expressions. So what I want to do in the time I've got available, and you can just stop me when it just gets too boring, but what I want to do is go through some of these tools. Some of them are going to be more familiar than others, but I want to talk about the ones that I think you probably won't have come across, because they're kind of interesting, and they solve some problems that have been very hard for cognitive scientists to resolve. So these are my favourite ones, the genetic tools. So if you think about emotions as evolved responses, then that sort of suggests that this is immediately off the bat a good place to start thinking about applying genetic tools. So what you can do is you can use genetic markers to study populations of neurons and not just study them, but manipulate them and measure them. And we're really talking primarily mice here, a little bit of rats, not higher animals. But this is one of the reasons this is such an interesting area, is because there are so many commonalities between emotional responses in non-human animals and in human animals. So it allows us to use a full range of the toolkit. And many of the neural structures as well in human emotions are pretty phylogenetically primitive. All right, so knockout experiments are one kind of tool. So what you do in a knockout experiment is you take a functional gene and you replace it with a non-functional one in stem cells, and then you replace the modified cells into a developing embryo, and you breed your knockout mice. Don't try and you could try and knock out rice, but it's not going to be that interesting. So what it does is remove that whole genetically determined behavior, that whole genetic trace, and then you can study how behavior changes as a consequence. So there are famous examples where you can increase anxiety levels in mice by knocking out the receptor for serotonin. And obviously when you do this, you have to operationalize the notion of anxiety, and I'll talk a little bit more about that in a minute. Standardly, people think about it in terms of bodily, somatic, autonomic responses such as body temperature and increased heart rates and so forth. So how am I doing for time? I've still got, an hour?
You have done 25 minutes.
Okay, perfect. I should be able to get through. Excellent. All right, so just out of interest, has anyone here ever heard of optogenetics? Okay, Philip has. Good. All right, so that's not bad. So the cool thing about optogenetics is, actually, let me just take a step back. So one real challenge that has always bedeviled cognitive science is the lack of tools for studying populations of neurons. So we've got good tools for studying individual neurons or very small groups of neurons. You can use electrophysiology, and you can do it in humans during surgery and stuff, but typically in animals. And then we've got large-scale tools like functional magnetic fMRI scanning and PET, and this allows us to see really large-scale activations of changes of blood oxygen. But if you think about a connectionist network, or the sort of thing that might be modeled by a connectionist network, it's going to be the size, it's going to be a population size that is in between what's studied in neuroimaging and what's studied at the individual neurons. And we haven't got any tools really for studying those directly. But actually these genetic engineering tools allow us to do that, because what you do in optogenetics is you change the genetic profile of a specific population of neurons by adding a tool that is light sensitive. And then that allows you to activate or deactivate that population of neurons by adjusting the light. And you can do this using drugs as well. And another thing that's particularly interesting here, so you essentially engineer some genes that will be sensitive to specific drugs. Another problem that you get in studying the brain is the problem of levels of temporal resolution. So we've got things that will allow you to study really detailed moment by moment changes like ERPs, single neuron studies and stuff like that. And then we've got slow things like fMRI, because that only reflects changes in blood oxygen level, which don't really happen all that quick. And what's interesting is that optogenetics is really quick. So you can just switch stuff on and off, whereas pharmacogenetics allows you to do much more long-term changes, and it's actually a way of artificially inducing lesions. All right, and so we've also got some other tools for measuring neuronal activity. So the technique here, the stuff is, it's pretty cool. So the stuff here is to engineer some genes that will indirectly measure neuronal activity. So functional neuroimaging measures blood oxygen, the bold signal, blood oxygen level dependent signal. No one really knows what exactly that maps onto in neurons, and what neurons are doing. There have been some interesting studies. But what you can do with genetic engineering is put some different measures, build them right into the neuron's genetic code. So you can measure calcium, you can measure changes in calcium or changes in voltage, both of which are correlated with different types of neuronal activity, and then you can measure these through an optical microscope. So you've got this whole toolkit that will allow you to start manipulating and studying neural populations. And then you can also use lesion studies to look at larger scale facts about the organization of the mind. You can use lesion studies to try and identify kind of like a fear network or whatever. And some of these lesions are the results of brain injuries in patients, and we'll talk about some famous ones in a minute. But some of these you can induce in animals. And you can induce them on a permanent basis, by surgery, or you can do them in reversible ways. So you can do them pharmacologically. Cryogenic is basically freezing. You cool the tissues down, and that decreases neural activity. And you can do it completely non-invasively using transcranial magnetic stimulation, TMS. So another completely different set of toolkits, different set of tools. So what I want to do in the last part of this talk, I think roughly the last third or so, is work through a specific example, probably the affective state that has been most comprehensively studied by affective scientists, and that's fear. And what's interesting about it is it really involves pretty much all of the tools that I've mentioned. So in animal studies, involves a lot of animal studies work, artificially stimulating different neuronal activity, creating experimental lesions, both reversible and irreversible. It also involves this kind of cool technique of fear conditioning, which I'll talk about in a minute. And then we've got a lot of we've got some human studies, some very influential ones from neuropsychology, from the study of brain damaged patients, but we've also got some pretty cool experiments from neuroimages. So let's start with fear conditioning. So here's a problem. You want to study fear. How are you going to do it? One way would be to induce fear in people or in animals, and then see what happens. But it's not that easy to induce fear, and sometimes there are some ethical issues about really scaring people badly enough to get interesting results. So at least in animals, one very standard technique to solve this is to condition a fear response, to use fear conditioning. So the way this works is that it's like any other sort of Pavlovian conditioning. You take a behaviorally neutral conditioned stimulus, which might be a flash of light, a puff of air, or a sound, and you match that with an aversive stimulus, like an electric shock. So what happens after the training is that you can get the fear responses without having to create a threatening situation. Because creating a threatening situation is going to create lots of potential confounds. And obviously there are some assumptions here about the nature of fear. It assumes that fear is a functional state, that whenever you've got fear behaviours, that those are the behaviours that are caused by an internal state of some sort, a multidimensional state that is acquired in normal situations. So what you get with the conditioned response is exactly the same as you would in the unconditioned response. And it also assumes, like all of these animal studies, that there are reliable behavioural markers of fear. So I want to talk a little bit about how fear conditioning is used, but first I just want to show you a kind of graphic that I made, or a table that I made, illustrating some of the behavioural measures of fear that are used in animal models. And it's kind of interesting because the DSM is the Diagnostic Statistical Manual, very influential tool for diagnosing psychiatric disorders. And it's got a bunch of criteria that are criteria for generalized anxiety. And it turns out that the measures of fear in animal models are really closely related to the DSM criteria for generalized anxiety. And there's another point here, which is that we were talking about fear and now we're talking about anxiety. And that's a reflection of that point I made right at the beginning about the real blurriness of these affective states. So I won't go through them all, but you'll see that, there's a classic measure of fear in animal models. These are not super pleasant, by the way. Is you measure the stomach upset, the stomach ulcers, and that's directly related to the human diagnostic criterion of having an upset stomach, diarrhea, defecation, pounding heart, which you can measure increased heart rate. So physiologically speaking, there are some pretty close parallels between the human case and the animal case. So one of the things that has emerged from multiple different directions in the affective science of fear is the importance of an area of the brain called the amygdala, which is a subcortical part in the limbic system, which is a pretty primitive part of the brain. And it's got a lot of anatomical projections, i.e. it's connected anatomically to areas of the brain that are directly involved in precisely these kinds of somatic markers of fear. And we can study it in many different ways. But in particular, some things that have been very influential are studies using electrical stimulation and also a complex of different types of lesion studies. So here, for those of you with excellent eyesight or maybe an iPhone 13 zoom lens, is a sort of graphic illustrating some of the connections. So I'm not going to go through them all, but you'll see that here are certain behavioural criteria for fear. So we've got again our stomach ulcers, urination, and so forth, brachycardia, which is a very rapid heart rate, and that's generally thought to be this kind of area of the motor area, the dorsal motor nucleus, connected to the amygdala. We've got facial expressions of fear. Those are in the face, the facial area. Again, that's connected up to the amygdala. The hypothalamus is thought to be responsible for corticosteroid stress response kind of things, very closely connected to the amygdala. So there are all sorts of reasons for thinking that the amygdala is important prima facie from an anatomical perspective. But again, another really important thing about studying the brain is that anatomy is not necessarily a super good guide. An anatomical connection doesn't necessarily tell you about a causal connection or information flow kind of connection. So that's where the experimentation comes in. And the experimentation involves both conditioned fear stimulus, so putting people in front of a large snake, for example, and the unconditional fear stimulus, which is, you know, the puff of air or the tone that has been conditioned. All right, so
You have 5 minutes left.
5 minutes? Come on, you're kidding. Okay, so lesion studies in rodents. Okay, that's good. It's all good. So what we see in rodents is that the amygdala seems essential for fear responses. So when you take fear condition rats, and then you lesion the amygdala, take it out. What you find is they no longer display the freezing response to the original stimulus, to the neutral stimulus. And a nice example here is that when you lesion the amygdala, your rats just they stop getting scared of cats. So they start, you put there's a lot of suffering here, but so if you've got a sedated cat, then the rats will just happily wander all over it, which is not your standard rodent behavior with cats. And there's a lot of good, interesting studies of amygdala damage in humans. So a very famous patient called SM who had amygdala damage caused by something called Urbach-Weither disease. And she just shows no fear responses. So classic day out with patient SM is you take her to the haunted house at the amusement park and it's like, whatever, cover her with spiders and she's perfectly happy with it. She wants to pet the snakes and, she just really is not responding in the way that most people respond to standard scary stimulus. But what I want to emphasize, again, a lot of people think, hey, the amygdala, that must be the fear area. But there's actually some really interesting internal complexity to the amygdala. And in particular, there are 2 bits that seem to have play different roles. So we've got the centromedial amygdala and the basolateral amygdala. And you get, SM has damaged both of them. But if you just damage one, you get completely the opposite set of symptoms or characteristics. So you get fear hypervigilance as opposed to fear hypovigilance. So hyper means intensified and hypo means absent. So SM is fear hypovigilant, but patients have been studied with damage only to the BLA, and they just really overreact. So you show them something mildly threatening and they just go full, they go full samurai on it. And what it seems to be the case is that the BLA is controlling and regulating fear responses while the CMA is a kind of reflexive generator of fear responses. So you've got a generator and you've got a regulator. And I'll skip that. That sort of pattern is writ large in what people sometimes call the human fear network, which has the sort of generating areas here and the controlling areas here. So that's the ventromedial prefrontal cortex, which is thought to play an important role in a whole bunch of higher cognitive functions, folk psychology and so on, but also seems really important in regulating fear responses. So since we're running out of time, I just want to show you one interesting slide. So I mentioned it's hard to do neuroimaging of fear because you want to study fear. You don't want to study people's concepts of fears, so you want to put them in a threatening situation. But how do you do that in a scanner? I don't know. I've been in a scanner. I find that threatening enough. But so how do you produce extra threat and extra fearful stimuli in the scanner? So here's a pretty cool experiment that was done by Dean Mobbs. Dean is his first name. He's not a real name. I'm a real Dean. He's not a real Dean. Okay, so what he did was he put people in a scanner and put their left foot, in the last of a little series of boxes. And then in the scanner, what the people saw was a large tarantula being placed in these boxes. So then you measure the response as the spider approached the foot. Of course, there's no spider, right? This was a pre-recorded video. I think it would have been hard to get that one past the institutional review board. But the people thought that there was a spider there, and you got some really interesting patterns of activation. So, for example, if you place it closer to the foot, you get massively augmented activity throughout the fear network. When you look to see what the amygdala does, well, the amygdala increases in activity whenever there's approach, but it doesn't matter whether the approach is from here to here or from here to there. So what the amygdala does is seem to be measuring increasing fear, but not necessarily the extent of that fear, assuming that it's more scary to have something here than there. And then you've got, again, activity in the singular cortex and the prefrontal cortex, slightly different bits of it, but as the spider moved further away, so that suggesting that these are the areas that might be responsible for controlling and regulating the fear. So I think I've got 1 minute left, so I will use my last slide to raise some questions, which maybe we can come back to in the discussion. So I've given you an extended case study of fear, but it will not have escaped your notice the reason why this lends itself so well to animal studies and lesion studies and seeing what goes on in mice and knocking out genes and so forth, is that it's a very evolutionarily primitive and relatively unsophisticated affective state. I mean, there is really a sense in which fear is, you can say there is something that is common to at least rodents, if not insects and human beings. How do we scale this kind of multi-dimensional, multi-tool approach up to affective states that are less evolutionarily primitive? And so, connected to that, how do we model the cognitive dimension of affective states? And how do we do that in a way that we're really talking about the cognitive dimension of affective states, not our understanding or language that we use to think or talk about emotions? And then something that I mentioned earlier, but I want to come back to it just to close off, is how revisionary is this relative to standard folk psychology? If you start thinking about affective states in this multidimensional way, if you think about them as complex multidimensional entities that have really important commonalities across animal kingdom, how far have we moved away from the idea of emotions as discrete psychological entities that are causally defined in terms of their typical causes and their typical effects, and representation carrying vehicles and so on and so forth? So let me just leave you then with those questions and look forward to hearing any comments or any further questions that you yourselves might have. Thank you.
Thank you, Jose Luis. So we go to the questions. Please raise your hands so I have an idea of how many people want to know. 1, 2, 3. Okay. I remember that you can ask in Spanish if you want. Esteban.
Thank you very much for your talk. Well, I have 2 questions, very brief. The first one is if you could say something about the applications of this to ethics in general, or animal ethics in particular. And the second one is about not particularly about the cognitive dimension of affective states, but perhaps more about the interactions between cognitive states like perception or understanding something, or having the thought of, for example, not like not expecting something, which could be very like surprise, but as a belief could be very closely connected to fear, for instance. Thanks.
Okay, so lots of things there. I mean, great points, great questions. So on animal ethics, I assume you mean animal ethics as in how we think about animals, not animal ethics as how we think about animal experimentation. Okay, well let me take I have conflicted views on the second. So let me talk a little bit about the first. I mean, there's a long-standing tradition in thinking about ethics of non-linguistic creatures, whether it's human infants or fetuses or animals, in cognitive terms. And I contributed to that myself with some work I did on the cognitive sophistication of neonates and the idea that birth is something that marks a natural distinction in moral terms. And I was highlighting particularly the importance of self-consciousness. And I think that in the light of all of this stuff that I've been looking at here and talking about, that kind of cognitive bias in ethical thinking is probably not the right way to go. I mean, we need a broader set of criteria for thinking about whether some kind of life or some form of life is morally valuable. But I do think that what we see is a scale and different positions on that scale rather than cut and dried, discrete criteria. So not a super helpful response. I think surprise is really interesting, and surprise falls into the general category of epistemic emotions that have been studied quite a bit from a philosophical point of view. And one reason I think they're interesting is because one of the things that's raised by epistemic emotions is how reflexive they are. That is to say, to be surprised by something, do you need to be aware of your expectation? Or is it enough to have an expectation thwarted? And debates about how far down in the animal kingdom you can find epistemic emotions that directly turn on that question about how reflexive they are. So, thanks.
Penelope.
Thank you for your talk. My question is, how is the current integration of affective science with enacted, embedded, embodied, extended cognitive perspective? I'm almost sure I pronounced it wrong, sorry for that, in the so-called 4EA cognitive science.
So, in some respects, I think there's a lot of continuity and compatibility. So, in particular, if you think about cognitive state, emotional affective states as multidimensional states, that often that's something that could be modelled in many ways in terms of dynamical systems. For example, a dynamical system is essentially a system that varies on a small number of parameters. So dynamical system models of the emotions would be an obvious way to go, and that's an important instigator that's an important driver, an important comparison, important theoretical tool for a lot of the 4E stuff. But we do have Robins, Philip, who's pretty knowledgeable about this stuff. So maybe you can come in at this point, Philip.
So the issue is about the fit,
Yeah,
between this work
and 4E.
Yeah, well, I think it depends on what E you're talking about. I mean, and this actually I wanted to ask at Rodrigo's talk, but I didn't have a chance. So I think that last E, which I think of as the extended one, is one that probably doesn't fit very well here. In fact, I don't think it fits very well with any aspect of cognitive science, including non-affective cognitive science, which maybe we can talk about that a bit. But I mean, there's a pretty clear sense in which there's a very good fit here with embodiment, right? Because that's what's central. What's most sort of clear about what's happening in affective science is the attention to somatic states, and also just a deep attention to what's going on in the body more generally, and that has been the foundation for certain kinds of mental phenomena. Affect being a particularly good example of that. So if we get to the other E's, I guess, what else do we have? We have enactivism. A little less clear, I think, in that case. Similarly with embeddedness, right? I'm not sure what I would say about that. But the E that sort of sticks out as one as being really clearly engaged is the embodiment one. That's how I see it.
Great, thanks for answering my question, Philip. I'll outsource maybe some other questions too.
Ella arriba. No sé, ¿alguien más levanta la mano por acá?
And then there's one here.
Okay.
Thank you so much for your talk. I want to ask you about the explanation or explanatory model of affective cognitive science, because much of what you what was exhibited there was about neuroimaging and neuroscientific evidence. And would you say that the affective cognitive science presupposed an integration between neuroscience and psychological explanation rather than an autonomist approach?
Absolutely, absolutely. And if I can't think of a word beginning with E that captures that, but this might be the fifth E that should be taken into account, which is the idea that we're finding really important and non-implementational levels of really non-implementational forms of understanding psychological phenomena by direct attention to neuroscience, and it allows us to fractionate and to make distinctions that we couldn't do otherwise. So, for example, I think that stuff about the distinction between the two roles of the amygdala is kind of really important way of articulating that complex state of fear in a way that we might not have been able to do without looking at the consequences of neural behavior. And likewise, the things that you can do by directly manipulating neural populations are just giving us a way of stripping away, of going deeper and more fine-grained than our regular emotional concepts, and studying them, just things that we wouldn't see if we thought that there was an autonomous level of psychological explanation that was tied particularly to our pre-theoretical folk psychological concepts of emotions. If we start with that, then it's like we're putting blinkers on.
Thanks for the
And there's
talk.
one more, we mustn't forget this one here, because that's been there right from the beginning.
Aquí ahí subimos.
It's a question about a sociological question about the state of the art. When you say from cognitive science to affective science, do you mean that now the core of the discipline is dominated, so to speak, from affective science?
No, I do not. That was a provocative title. What I meant to say was, what I really should have said, but it just didn't fit so nicely on the slide, was from traditional cognitive science to affective science. So I think of affective science as clearly part of cognitive science as it is now, but it's also, I think, clearly engaged in a different sort of enterprise from the cognitive science that was prominent in the 1970s and the 1980s, tied with the computer model of mind, with theories of representation, with theories of content, with worries about mental causation, autonomous explanation that took Ma as the prime example. I mean, all that stuff is, that's in the rearview mirror.
Okay, so it relates to cognitive science as like a parallel subdiscipline, or that's what I don't get. I mean, the analogy was in the 80s, like cool kids did flutter. So my question is, do cool kids now do affective science, or it relates to cognitive science as, for example, economics of, I don't know, developmental economics relates to economics?
I think somewhere in between the two. So if you said to me, where are the most exciting things? Hey, you say, hey, you write textbooks. Where are the most exciting things in cognitive science? I would say at the moment it's probably the application of deep neural network techniques to study object perception. It's the integration of neural networks into autonomous vehicles. It's affective science. It's all things that are not clearly related to the physical symbol system hypothesis, the language of thought, and all that stuff that I predict is going to be gone by edition 7. You heard it here first.
We have little time left, so I'm going to join the last. So you can talk, and there you can talk, and you want to add something.
I'm fine. We can
Okay,
talk
so
later.
you just make your questions, and then you will answer all together.
Oh, okay, interesting. All right.
First of all, thank you for the presentation. It was really informative. I learned a lot. 2 questions. I wanted to know if the current state of art of these kind of investigations has considered a few gaps that can be left when standing from certain philosophical point of view. For example, when studying the reactions of some animals like mice, we are only considering the external causation, but not the internal causation of the brain interacting with other parts of the brain. So we're only understanding affective states as reactionary to external sources. So does the present state of the investigation takes into account that and other gaps, for example? The differences that may exist between the anatomical, let me say another word, between how men and women in human species are differentiated in terms of anatomical positions or the morphology or the function of some organs, because from things I've read about how we react to things like heart attacks and the symptoms, we see that women has a different frame of symptoms related to men's symptoms. So I wanted to know how is that taken into account in this kind of investigation. And the second question is, how do you think cognition?
I make this 4 questions so far.
That's
Yeah.
good. Yes, so give the microphone to
Oh, okay, thanks.
I'll just say one thing quickly before I forget. So
the problem is we don't have much time left, so I prefer to
It
them to
is very connected, so I think you can respond both. Mine is like when we feel like we can rationalize or affect our own emotions by thinking about them, processing them, and how is that something that will be studied in this case? Like, are we really affecting our emotions with internal process, or is just reactionary about that?
Yeah, you can then answer that.
Okay, I'll answer both
so
of those.
The
So-
microphone will go up, but you can answer.
So just to talk about the mice. So in the kind of thinking that gets us to this idea of a fear network with different parts of the brain doing different things and the regulatory function being taken by the anterior cingulate cortex and the prefrontal cortex, that comes when you move away from rodents and you start looking at human lesion studies and human neuroimaging. And what I think is interesting is just really interesting is trying to bring those 2 things together. That's what's so exciting about this area. But I should also say, relative to your question, that this is pretty embryonic, this stuff. I mean, there's been quite a lot of work done in fear, but fear's an outlier in a lot of ways. It's really so much simpler than a lot of other affective states. And the idea of regulation, conscious regulation of emotional states, has been studied. But it's been studied, I think, more by social psychologists and clinical psychologists rather than by these folks. So, you know, not quite so scientifically motivated. It's more from a kind of clinical perspective.
Okay, so the last question.
I think this one will be short. Thank you very much for your conference and for your work, which I'm now using to reintroduce myself more rigorously into cognitive science. So thanks for that too. What do you think is the prominence or importance of emotional life, or the emotional aspect of mental life, to our cognitive mental activity more generally? Do you think there is some necessary connection between them? For example, could you, in principle, build an intelligent machine, a general artificial intelligence, without emotions, without conscious experience of emotions or emotional states whatsoever? Or there must be some necessary connection? So is there, for example, some connection between these models of architectures or models of emotional activity and traditional architectures for cognitive activity? It's sometimes said that emotional and cognitive life are structurally intertwined, both at the neural and the subjective or phenomenal level, if you like. But what do you think about that?
I'm inclined to agree with that. And it's too big a topic to go into here, so I'll just say one thing, which is I started out by mentioning Herbert Simon and his idea of emotions as interrupt mechanisms. And one of the things that I think is so interesting about that paper, which has largely been neglected, is that essentially what he's saying is that a computer needs emotions, right? A real-time computing machine, a real-time computing organism needs to have some sort of mechanism that will interrupt in response to external stimuli and meeting survival-based needs on a time, on a real-time framework. So for Herbert Simon, the father of cognitive science, you can read him as saying that a computational machine needs to have emotions. He didn't have a whole lot to say about qualia and the feelings of emotions, and that's also something that has been left out of this whole discussion up to now. But for me, I think that looking at conscious qualitative experience, instead of focusing on perception, but shifting the debate over to emotions is probably going to be a profitable move.
Okay, with that wonderful conclusion, we thank you very much. And we will have a 10-minute break.